Okay, thank you very much for joining. So we have Dr. Sandy Brownlee from University of Stirling. And Sandy will be talking to us on the topic improving trust in the results of search-based optimization. We use a lot of search-based optimization techniques within the company, mainly in our field engineering space and also in our network design and planning area. And we have been actively looking at how we could improve on the way we explain these algorithms. We do have some PhD projects with Sandy and the data lab in Scotland together with RGU on this. I mean, some of the Sandy students are on the call and others who have worked with us in the past as well. Dr. Ken Reed around Rust optimization are also on the call. Please do use the chat to post your questions, and Sandy will talk around 40 or so minutes and we'll open up for questions. Over to you, Sandy. I encourage that we all go on mute and off camera as well. Thank you.
Having a muted audience is a good deal different to when we're dealing with students. It's great. Thank you, Gilbert, for the introduction, and thank you for inviting me to do this talk. This has been a topic I've been interested in for quite a while. I've been very interested in real-world applications of optimization, usually genetic evolutionary algorithms, and my view is very much that if person doesn't trust the solution that they've been given, then they're not likely to use it in practice. And so then what's the point of having actually done all of that work in optimizing in the first place? So that's really what the thrust of the talk is about today. And really just baby steps in that direction, but we'll, hopefully it's helpful to everyone here. I'm also very bad for this on video calls. I'll probably be pointing at my screen, so if it looks like I should be telling you something, please pop up in the chat and actually say what on earth are you talking about. So let's convince PowerPoint that it wants to listen to me and give you an outline. So I'll give you a quick recap of what evolutionary algorithms are all about. I think most people here probably know, but just to make sure we're on the same page. And then a little bit about what happens when it goes wrong. So why we might not trust the solutions that they're coming up with. And then the rest of the talk is really examples. So it's some different techniques that I've tried with different real world applications. None of them are specific to BT applications. I'm hoping that'll change since we're doing a bit more work together again just now. But I've got a couple of tangible problems to do with building design and improving simulation software. And I hope the lessons from those are general enough that we'll be able to apply them to some BT problems too. So a little bit about evolutionary algorithms before we go any further. So we have this idea that we've got an optimization problem and we're looking for solutions to that optimization problem. And it might be a scheduling problem. So, applying engineers to different jobs, and or it might be finding the parameter configuration for a model, or designing an engine part, whatever. So we've got this idea that there are things that we can change that we call variables, and by changing those things we produce a solution to that problem. And it might be good, it might be bad, but we've got some concept of quality of our solution. So we have an example here of a few solutions. The rows here, each row is a solution, and I've kept it very simple. The variables are just ones and zeros here. And over on the right, we've got our measure of quality. So that might be cost or performance or something in the real world. Here, it's a really trivial toy problem. It's one that GA and evolutionary algorithm people play with all the time. We're just counting the number of ones in each solution. So the best solution would be to maximize that, be all ones. So this one's not bad. It's got 4 ones out of the 6. The one at the bottom is not very good at all. And the way that the evolutionary algorithm works is that we'll pick a couple of the best ones and take copies of them. We'll mix them together somehow. So it might be as simple as just picking a point and swapping them over, as I've done here. Might be a bit more interesting than that. We call that crossover. And we'll mutate one of the some part of the solutions as well, usually to try and add a bit more variety into the solutions that we're making. So we made a couple of solutions. Lo and behold, one of them happens to be a bit better. So we got a 5 there. One of them's not so good. It's a 3. We might throw that away. But we'll repeat this process. We'll generate more solutions. We'll replace the old ones. And over time, this population here, come on, mouse point, there we go, is going to converge on what we hope are going to be really good solutions. And this works really well for a lot of quite difficult combinatorial and parameter tuning kind of problems. Usually things where we've got a very large space, a lot more than 6 variables. And that's great. You know, they work reasonably well, and we've got a solver for all kinds of problems. The issue here is that the algorithm's designed to maximize fitness or potentially minimize fitness, depending on what the problem is. But it's going to do that however we have defined our problem, however we've defined our concept of fitness, our quality measure. So often we don't actually formulate that fitness function very well. We maybe got in mind some other things that are implied about what we'd like a good solution to look like, or it might be that we've just not actually captured our idea of what a good solution looks like. Or possibly there's kind of something subtle going on that we just hadn't realized when we defined the problem. And that can lead us into a bit of trouble. Machines are really good at finding shortcuts. They will find holes in the definition of the problem. Anyone who's worked in optimization problems will have probably come up with some solution that they didn't quite really want at some point. So I've got a couple of kind of amusing examples here that are drawn from the evolutionary computation literature. You might be familiar with them, but I'm going to share them again anyway. So the first one was that a genetic algorithm was being used to evolve designs for a robot. So it was looking for different components like legs and joints and motors and things, assembling them together and trying to make a robot that was supposed to travel as quickly as possible across a space. And what happened? Well, usually I would ask for suggestions from the audience, but that's not all that smooth in this environment, so I'll just tell you. What happened was we ended up with, and I say we, this isn't my work at all, but what happened was that the robots that were evolved had giant legs, and they were designed to stand at one side of the space and then just fall over. So crossing the space incredibly quickly, much faster than anything with little legs running across it could have done. So not exactly the kind of solution to the problem that was actually being looked for. It was still a solution to the problem. It still solved the problem of getting across the space quickly. It just didn't do it in the way that was anticipated. Another example was from an evolutionary algorithm that was creating agents for noughts and crosses, or general noughts and crosses game. So in this game, we've got a grid as we do in regular noughts and crosses, but we are trying to get 5 in a row, and the grid is as big as you want it to be. And what happened, if you're a speed reader, you might have spotted from the text here, is that the fitness here was trying to beat as many AI players as possible. And the way that the evolved agent did that was by simply placing its mark as far as it possibly could away from the starting position. And that caused the opponents to run out of memory and crash, so they forfeited the game. So not strictly speaking a gaming strategy, rather kind of a bit of a workaround. One more example, this is something a bit closer to some work that I've been doing, which is to do with using evolutionary algorithms, again, to improve software and to fix software. And here, the idea was to fix very simple sorting algorithms. So we've got an algorithm, it's trying to sort numbers into ascending order. And the evolutionary approach is being used to fix a bug in that. And the cost function, the fitness function that was being applied to that to guide the search, measure the quality of our solutions, was simply looking at the pairs of numbers in the sequence that was being returned and saying, well, if the neighboring pairs are in the right order, then we've got a 0. And if they're in the wrong order, so like in this one here, they're descending instead of ascending, we'll add 1. So there's 4 neighboring pairs here, so we've got an overall cost of 4. This one's a bit more random, so we've got a cost of 2. What shortcut did you think the algorithm managed to find here? Again, it'll have to be a rhetorical question, I think. So I really enjoyed this one. So once again, the algorithm has found an answer. It's just not the one we were looking for. So there was a problem with the definition of costs here. We needed to check that the original numbers were actually a part of it as well, that we actually sorted the sequence. We haven't just found a workaround. So the algorithm's just looking for patterns that can maximize or minimize our goal. How do we know then when it's exploiting a loophole in our definition? How do we know that we can trust the solutions that we're being given and that they've not just found a workaround or a shortcut for our definition of the problem? Well, maybe we could run them all by a human expert. So we could just give them to someone very clever, and they'll look at the problem and go, oh yes, that is a really good solution to the problem. Well, there's at least a couple of issues with that. One, it's kind of defeating the point of having a machine doing a lot of the work for us. But 2, it's actually the case that a lot of these problems have enormous search spaces. It's really hard to visualize a space like that, and to know whether we've actually got anything that's as good as it can be. That is why we are using these search-based approaches, evolutionary approaches, to try and find the answers to the problems. So we need to do a little bit better than that. And this is where the topic of explainability comes in. So you probably heard this term. It's hot topic in machine learning, really. So there, we're looking at taking deep learning algorithms, artificial neural networks, this kind of thing, where you've got essentially a black box. As numbers go in, or pictures go in, or text goes in, and then out come classifications. You know, this picture is a dog or a cat, or maybe more seriously, something like this image is of a cancerous tumor or not, or this looks like an insurance fraud, or we should turn down this person's mortgage, that kind of thing. And explainability is all about trying to interrogate those models and say, well, why did you come to that decision? Why did you say this person should have their loan rejected when that person didn't? What features were driving that decision? You know, was it that the person is from a poor background, or is it because they've actually got a history of defaulting on their loans in the past, or something like that? So it's about trying to open up the black box. It's trying to understand what relationship there is between the kind of input data and the classification that's coming out from the algorithm. So how can we do this for search and optimization problems? And obviously for some, particularly if you're using a conventional mathematical optimization approach, you've got a clear formulation of the problem. We're already quite a lot of the way there, but with these kind of slightly more fuzzy kind of approaches, randomized search algorithms like evolutionary algorithms, they're exploring the space and they're kind of learning about solutions as they go, implicitly learning, that is, they're kind of storing information about about the problem within the population. How are we able to interrogate that to see what they have actually learned? Is it just random chance that they've stumbled on a good solution, or is it more than that? So here's a few of my thoughts on this. It's really about trying to understand what's needed to make a good solution, at least from the perspective of the algorithm. What has it learned about what good solutions look like, and how do the solutions that they've generated, how do they satisfy those criteria? How robust is the solution? So can we tweak it if we don't like some bits? So let's say we are doing scheduling of a workforce, and we've got one engineer who's been placed right in the middle of the night at a terrible time to be working, and he wants, quite reasonably, to be changed to a day shift. Well, if we did that, is that person a really crucial component of the overall quality of the schedule, or actually could we get away with moving them around and it doesn't actually matter? In which case, well, let's do it. Let's move them to something that he'd be a bit happier with. maybe if circumstances change slightly, so the kind of operating conditions or the constraints around the problem change, would that break the solution that we've got? Is it very brittle? A lot of these things can be answered simply by looking for the relationships between the variables and the objectives. So, kind of what is the what we call the search space, the things that we can change about the problem. What's the relationship between that and our overall goal? And part of this is also about giving an informed choice. So maybe, and this is a very big open psychological question, maybe users will trust solutions if they've actually been involved in the decision-making process to some extent. So if they've been given some guidance about what good solutions look like, but then they've been given a selection that they can then kind of choose from, that is the point at which they might be able to say, well, oh, I forgot to tell you, but I didn't want to just satisfy the constraints of this schedule here. I also wanted to make sure that there was a fair distribution of work across everybody, or something like that. One of these implied goals. By including them in the decision-making process, they're able to play a much stronger part in choosing those solutions to match the genuine criteria that they've got for the problem. So there's a few ways to do this, and the rest of the talk is going to be covering a few approaches that I and one or two other people have been involved in doing. The first one is what I've got. Aidan, who's on the call, his PhD student, is looking at this topic just now. Some of this goes right back to my PhD work, and it's about mining what are called surrogate fitness functions. So a little introduction to what surrogates are first. Here's a typical workflow for an evolutionary algorithm. You've got an algorithm on the left, and it's generating solutions. And each one of those is being passed to a fitness function or a simulation or something that's measuring the quality of the solutions. And numbers representing that quality or fitness are going back to the evolutionary algorithm. And then the algorithm generates new solutions that hopefully improve that quality. The problem is that sometimes this can be really long running. So a lot of the building performance stuff that I've done, for example, you've got a very long running physics-based model that's running to compute the fitness of solutions. So we introduced a thing called a surrogate to try and speed the whole process up. So it's just adding an extra layer on here. We got the surrogate over here, and it's a model. It's trained using a machine learning approach. You've got solutions coming from the evolutionary algorithm with their fitnesses that you use to train this surrogate model. And then rather than calling the real fitness function, a lot of the time it'll just call the surrogate and say, well, how good does this solution look? Is it a bad one, good one, indifferent, whatever? And that will guide the evolutionary algorithm towards solutions that look promising, that we can then invest a bit of time from the real simulation on. So that's the idea of a surrogate. But the neat thing about this is that we've now got a model of the fitness function, and it's not just a model of the fitness function in general, it's a model of the fitness function that is very biased towards the solutions that the evolutionary algorithm has seen. So the algorithm has been trying its best to find good solutions for our problem, and that surrogate kind of encapsulates what it's learned about what good solutions look like so far. So maybe we could use an interpretable surrogate model like a decision tree or something else like that, where it's no longer a black box, so that'll give us an idea of what good solutions look like. Or it might be that we can use some of these explainable AI techniques on that black box surrogate model to try and learn a bit more about what the algorithm thinks of as a good solution. And what I would suggest, if it turns out that we're able to get some good explanations about what the algorithm is doing this way, it might be worth building the surrogate anyway, even if it's not for a speed up. So let's have a look at a couple of examples of using surrogate fitness functions. So the first one is using a thing called the Markov network fitness model. So this is straight out of my PhD work, which unbelievably is more than 10 years ago now. And Markov network is an undirected probabilistic graphical model. It was originally used as part of an estimation distribution algorithm, it doesn't matter too much what they are. In short, they are an approach where you take a genetic algorithm, and instead of having this crossover mutation stuff, the kind of biologically inspired way of making new solutions, you build a probabilistic model of good solutions and you sample that to make new solutions instead. But what we have in this model is essentially a linear model that relates variables and groups of variables to the fitness function, and we can use it as a surrogate. If you're not too happy with looking at a load of maths, then you may look away for a slide if you wish. But in short, the model looks something like this. Let's come back mouse pointer. There we go. So over on the right, we've got a representation of a 4-variable optimization problem. And the circles there, the nodes on our graph, are the variables, and then we got connections between them that represent interactions of some kind. So they might be things like you can't schedule two people to do the same job. So this is job one, this is person one and person two, and you can't schedule them both to do the same thing at the same time, something like that. And if you look at the model here, it's basically a bunch of terms, one for each of the variables, and then one for interactions between variables. So this is a term here for variable 0. This is a term for variables 1 and 2, the interaction between them. And we got a sum of these that equates these variables with weights associated with them to the negative log of fitness. And I won't explain why it's the negative log. It's rooted in the mathematics of how the probabilistic model is built. But essentially, we've got this model that connects one to the other. And we fit this model to some data. These alphas here are parameters of the model. We fit them to a population by taking existing solutions with their fitnesses and substituting them in here. And then that'll give us our model that we can then use to predict the fitness of solutions. And I'll give you a couple of toy examples before we go on to stuff that is, I think, slightly more interesting, just to illustrate the point. So that function that I had back at the start when I illustrated the genetic algorithm, that was what we call a onemax function. So there, what we're trying to do is set all the values to 1. Now, each one of those variables is of the same importance. So they're all contributing a 1 to the overall fitness. And if we look at the model that goes with this, so this here is actually a bar plot, and this is for a 100-bit version of the onemax problem. So we've got 0 to 100 along the bottom. Each of the bars corresponds to one of the alpha values in our model that we had on the previous page. And you can see that there's error bars on there. I've actually computed models over a few populations, so there's multiple models going on here. But you can see fairly consistently, all of these alpha values are coming out at being negative 0.009, something like that. They're all around about the same, and they're all negative. Now, the mathematics of how that model works basically tell us that if those alpha values are negative, then it says that the global optimum should be a 1 for that variable. So what this is saying is the optimum for the onemax problem is to set all of the variables to 1, which is something that we knew, but it's reassuring to actually see that coming out. And it's saying that all of the variables are equally important. What's really cool about this is it was trained on something like 110 solutions. So it had actually learned that much more quickly than genetic algorithm would have probably solved a problem of that size. Another toy example is what's called the checkerboard problem. So that's to take those binary variables and arrange them into a grid. And here we're counting whether neighboring squares, neighboring variables in that grid are different to each other. So we end up with 2 global optima. One of them is like the checkerboard on the left and one's like the one on the right. So you can imagine that maybe blacks are 0s and whites are 1s, or the other way around. It doesn't really matter. So we got 2 global optima this time. And if we plug that into our Markov network model, and we get our coefficients back out, we get 2 sets of coefficients. And I should say one of the flaws of this whole approach is that you've got to choose which terms you're including in the model. Otherwise, it can get very computationally costly. that's one of the things that is unfortunately in that black box of future research. But what we've got here is two sets of coefficients. On the left, we've got what we call the univariate coefficients, and you see they're all floating around about 0. What that's telling us is that for each one of the variables, we don't care if it's a 1 or a 0. We really are not fussed either way. The ones on the right are the coefficients that go with what we call the bivariate terms. So these are the neighboring pairs in our grid, and they've all come out as positive. And the mathematics behind the model will tell you that if you've got a pair of variables and the coefficient that goes with them is positive, then that means they should be different in value. So it's found some information pointing towards the global optimum for our problem. You can also see that some of those coefficients are twice as big as others, like these bars up here compared to these ones down here. And it's very simple. All that's going on there is it's identified the ones in the middle of the grid. It's found the ones that are most likely to impact on fitness, because if you change one of these variables, it's going to impact on a couple of it's going to impact on fitness in more than one way, rather than the ones at the edge, which don't really matter so much. So it's identified where the kind of important region of that grid is as well. Let's try going to what I tend to drolly call a concrete problem, because it's in building design. I'm very glad that I can't hear the groans that go with that. So this is about optimizing the performance of the design of a building, and the building on the is the one on the right here. It looks an awful lot like a couple of offices I've worked in over the years. Very straightforward box with a grid on the side, and that grid can have each cell either being glass or not glass. And what we're trying to do is find an energy efficient design for this building. Essentially, if we've got loads of glass, we don't need to run the lighting so much, but probably we're going to need to run the air conditioning lots. And conversely, we won't need to run the heating system quite as much in the winter because the sunlight's coming in. But maybe if there's lots of glass, then lots of heat's going to leak out. So there's a bit of a complicated picture going on here. And I'll just answer that question that's popped up in the chat. When you train the evolutionary algorithm to get the surrogate, what training data do you use? And is this training data used to improve the algorithm? Yeah, so it's usually the case that you would use it online. So it's the solutions that have been visited by the evolutionary algorithm. So it is just the population, and it might be several populations worth of training data. You do have some examples where you just generate a whole bunch of solutions at the start, you make a surrogate for them, and then the GA will, or evolutionary algorithm, will run on top of that surrogate only. But usually it's solutions that are coming from the evolutionary process, and absolutely you can use them as part of the evolutionary search as well. I hope that answers the question. So what we're trying to do with this building design problem is minimize energy. And here's one example solution that's come out. Looks a bit like a flying bird or something. It's not a particularly attractive window. The blue cells there are the glass, and the white cells are concrete. And that's one of the minimal energy solutions. Now, there's a couple of things that we can do here, because we're really interested in trusting this solution, and it's kind of hard to trust that one because it looks a bit rubbish, doesn't it? Well, there's a couple of things that we can do. One of them is just allowing the user to know how robust that solution is, how much they can change it, tweak it a little bit to something that's just closer to what they want. And knowing how much of that is just down to the fact that it was a randomized process that produced this, and that maybe some of that is just statistical noise. So let's have a look. Now I'm going to take a step back from surrogates briefly, just because there's a really simple thing we can do. And that is to take that solution, so it's outlined with the dotted line there, and we can try just changing one cell at a time to either from glass to not glass, or from not glass to glass, and then measure the difference in energy performance. And each of the arrows here is showing whether we increased energy or decreased. So what we can see is this little bit here, the odd kind of inlet, the very first cell in that, if we change that to glass, we'll decrease the energy consumption of the building. So that's actually a really good thing. So we could get that by just doing a local search, and that's essentially what this is. But what we're saying here is to the user, we're kind of done with the evolutionary search, but if you change this one, you'll get a big gain. And actually, if you change all of these, you'll get a fairly small so you get a big gain in energy performance, so you'll decrease energy consumption. And if you look at these other ones here, there's only a small increase in energy if we change those to glass. So we can maybe flip all of these and we get much more satisfying, kind of still slightly odd because it's a bit round, but we get a much more satisfying shape of window. So the user's been involved in kind of refining that solution towards the end. The only problem with that is that it needs further fitness evaluations. And actually, if we combine some kind of local search method here, we're going to need a lot of further fitness evaluations, and they could be costly. So why not go back to our surrogate and try doing the same thing? So here again, it's applying the Markov fitness model to the solutions that the algorithm's seen. So this particular model I'm going to show you is coming from the 400 highest fitness solutions that were visited in the first 1,000 that were used by the evolutionary algorithm. And the model that we get out, we can then visualize it as a heat map. Oh, I'm not going to show you the heat map first. I'm going to show you them as a plot. I've forgotten that. So we've got two sets here. You can see that one set of them is positive and kind of has got a bit of an increase, and the other lot is all floating around 0. Now, the ones that are around 0 are the neighboring terms. These are for cells that were next to each other. So what that's saying is, if you add one piece of glass, it doesn't really make much difference on whether the cells around it are made of glass or not. They're all kind of independent of each other. But these ones here is saying something about some of the cells seem to be more important than others. So if we then put that into a heat map, and here we go, at this point, the algorithm hasn't actually figured out that they should all be glass. You can see there are no negative values, which would mean 1s rather than 0s, but it has got lots that are much closer to 0 than others. So the blue ones are basically saying, well, we really don't think that these should be glass. And the red ones are saying, well, we do think that these should be glass. And again, we've got that kind of patch of red in the upper right corner there. So it's saying, and a building designer would completely agree with this, it's saying that the glazing should be kind of high up and kind of all in roughly the same place, and that'll let the most light into the building without letting too much heat in. So that's giving some kind of an explanation as to what the good solution looks like. But more importantly, it's giving an idea of how much we can change the one that we've got. So how much can we fiddle with it and get it closer to what we really want. Basically, there's an aesthetic consideration here that we care about what the shape of the window looks like, but that was never formulated in the problem. And by having this information, we're able to make those changes with some confidence that it's not going to break the solutions too badly. So, oh yes, mining the surrogate, a little summary of what that's all about. We're generating these plots using evaluations that are coming from a surrogate model, which we kind of get for free because it was being used to speed up the search. And it gives us a broader view of what good solutions look like. On to another example now, and this is some work that I did with the airline KLM. They've got an in-house piece of software. Sadly, it's been retired now, so this is no longer quite as impactful as it used to be when I did present this stuff. But the idea here is that they have this piece of software that they put their flight schedules through to test whether they are robust. So what will happen is they will put in kind of 20,000 flights worth of scheduling into the simulation tool, and it'll do things like say, well, what happens if this plane breaks down in Amsterdam, or Heathrow is fogged under and nothing can fly there? How much is that going to break the schedule? Is there going to be a knock-on effect that causes lots of people to be late or delayed in some way? So that's what its job is, and it's basically part of a loop. So they generate schedules, they test them with this software, and then they go back and try more schedules. And what KLM asked us to do was to try and improve their simulation tools so that it was more accurate, it was better at predicting what really happened, and also faster, so that they could try out more schedules in the same space of time. This is a fairly simple parameter tuning problem. It's not a combinatorial optimization problem. It's simply changing a few dials and seeing whether the simulation runs better. So we got 14 parameters that control performance of the simulation, and these have been manually tuned over about a decade. Many of the experienced software developers will have seen lines of code that are, do not touch this bit, can't remember how this works, don't really remember what this does. Okay, the best of us do manage to avoid that kind of thing, but I know it certainly appears in my code from time to time. These things had reached a point now where you couldn't really improve the simulation any further by hand, not without an awful lot of work. So our job was to kind of go back to the start and try exploring parameter configurations more fully so that they can get a more accurate model. And they gave us some training data, basically some real world schedules and what happened in the way of delays and things with them. And we've got here, again, just a search-based approach. So we've got an optimization algorithm. It's generating parameter configurations. They get passed to the simulation tool. It runs for a while and gives us back an accuracy. And then we try another configuration. The tool we were using for this is certainly not my own work. It's by some very clever people who are named down at the bottom here, using a tool called SMAC, which is Sequential Model-Based Algorithm Configuration. Well, I missed the word algorithm out there. Very helpful. And it's a really nice tool. You basically write a wrapper for an existing application, and then it'll tune the parameters of that application. And the way that it works is internally it's got a random forest model. It starts out with a couple of possible configuration solutions that have been generated at random and fits the model to those. So it's essentially like a surrogate model approach again. It then takes the most likely solution from that model and tests that one. That might be an improvement, it might not, but it uses that to then refine the model, and it repeats that process over and over, adding more and more information to the model until the solutions that it thinks are likely to be good actually are very good, and it's able to stop. And using this tool, we were able to get some really nice results. These numbers are more or less meaningless, right? But their accuracy, their mean squared errors, we had a 271 and we got it down to a 241. The people at KLM were very happy with that. We'll come back to what we did with improving time shortly. I'm mindful that my grand promise of 45 minutes might be a bit optimistic, but we'll see. We'll keep going. So we were interested, as well as giving them these solutions, to explain kind of what was going on with them, because the developers of the application at the time were still actively involved in improving it further, and they wanted to know what the different configurations were all about. So we've got the surrogate model that's kind of sitting at the heart of that SMAC tool, and we're using a process that's called functional Anova, and it's basically exploring that surrogate model to try and find the sensitivities of each of the parameters, how much of an impact each variable, each parameter has on our overall fitness. And the way it works is roughly like this. Let's say we're interested in variable number 1. We have an equal number of each of its possible values. So we've got an equal number of zeros, an equal number of ones, and then the other variables are either set to just random patterns, or they are set to like a Latin square or something. So you've got a good coverage of the space of other values, other variables values. So we've got a bunch of configurations for variable 1 being 0 and a bunch for it being 1. And we've got some fitnesses that go with those. So we can then get a kind of general idea of what having it being a 0 and what having it being a 1 looks like in terms of the overall fitness. So we've got a range, we've got an average here, and we can plot that. So this is the stuff that we gave to the people at KLM. We said, well, look, there's this create gamma parameter in your model, and when it's true, we've got a performance this. When it's false, we've got performance this. So performance here is mean squared error. So we actually want the low values. So we probably want this create gamma to be true. Certainly this swap measure down in the bottom right, we want that one to be true, because that definitely looks like it's making performance better overall. Whereas other ones, like this one here in the middle at the top, doesn't really seem to make an awful lot of difference one way or the other. We're able to do slightly more interesting things than that, though. With the continuous parameters, so it is a sampling of the space, and we're not trying, it's impossible to try every possible value for a continuous parameter, right? But we're able to get this plot here for this one called ground factor out. And the reason that this is interesting is that in all the time that it had been developed, the recommended maximum value for this variable was here. It was 1.3, right at the edge of this cliff. And all of our solutions had come back with them being 1.6 and up. And it's very obvious when you look at this why that is. So we're able to give this kind of greater information saying, well, actually, it doesn't really matter what it is as long as it's more than 1.6, but it really wants to be more than 1.6. Equally, this max maintenance reduction, well, there's lots of kind of randomness going on there. Doesn't really seem to have much of a general impact on the performance, and that might be a reason to go back and look at the model. So one of the buildings problems I looked at a number of years ago, we had a thing come out and it looked like this, and it was to do with the air conditioning in one of the rooms, and it really should have had more of an impact on energy than that. And that forced us to go back and look at the configuration of the problem again, and we realized that actually we'd forgotten to connect up the air conditioning in that room, and that's why it seemed to be making no difference whatsoever. So it's helping us to interrogate what the algorithm has seen about the problem as well. So yes, we're showing the relationships between each variable and fitness, and that's giving us a reason for stepping outside recommended bounds or for choosing particular parameters for our process. Right, the last bit of the talk, hopefully about another 5 minutes or so, we'll see, is multi-objective. So this is looking for trade-offs. So multi-objective optimization, rather than trying to just minimize energy or maximize performance, things like that, we're trying to look for a trade-off now, where probably have got some kind of conflict between goals. Like with buildings, energy efficiency and capital cost tend to trade off against each other. You can either have an energy efficient building that costs loads, or you can have a cheap building that is really rubbish in terms of energy efficiency. And if we can identify a trade-off like this, then we're able to find sweet spots. So you'd be really silly to pick this solution that I'm identifying here. Hopefully you can see my mouse still. When you've got this solution here, you're saving about 2,000 kilowatt hours in terms of energy consumption, but negligible extra cost, right? So you're looking for solutions like that, but there's probably still other things that you would like to consider, the design considerations about what these solutions look like. Maybe you want to know what's driving this trade-off, or the things that I can change that are not going to move me along here. And there's a lot of factors to consider. Some of the earliest work on this is by a well-known researcher called Deb, and you can check that paper that I've identified there. I've done a little bit of work on this as well, and I'll highlight a couple of things, but that's the earliest paper that I had on it down at the bottom there. So I'm jumping back. Apologies for jumping between applications quite so much. But firstly, we'll look at the simulation software again for KLM. Here's the really neat thing that we were able to give them. This is their solution. These are the solutions we came up with. So what we were able to say is that by having used, so in this case, we'd used multi-objective GA called NSGA2. We've been able to find solutions that were much faster than their configuration. That's things like this, although they're not so good in terms of error rate. These ones up here, good bit better in terms of error rate, but much longer running. These ones here, though, these are better in both of the objectives. And we're really interested now in whether we can make something of this little trade-off that's going on here. As we move from higher error, faster running to slightly longer running, lower error. So what we do, again, it's just about taking these solutions from this pre to front, because we've got a set of solutions now, we're able to plot them in terms of the variables and the objectives. So we've sorted them. Each row here is a solution, and we've got ascending mean squared error and descending runtime over on the right. And then we can see how the different variables interact with those. So we've got things like this variable on the far left, MMR, doesn't really seem to be doing anything. It seems to be random noise across the whole lot. Whereas this one here, CMO, that seems to be all one. So it suggests that it's important for getting it close to the Pareto front. We might need to do a bit more digging to find out whether that's actually true or not, but it certainly looks like we want to keep that to be a 1 to stay in the optimal solutions. But we've also got things that actually change along the front. So this SMO seems to go from 1 to 0. CG seems to go from 1 to 0, and then when SMO changes, it goes from 1 to 0 again. So it's kind of a secondary driver. So we're then able to start saying things like, well, actually, I'd prefer to change one of these. Maybe it's got some implications for implementation or something. We're able to see which factors are really driving this trade-off between the different goals. And I'll show you another way now, which I promise this is almost the last slide. This is some work really done by Neil Urquhart and a number of others at Edinburgh Napier University. It's really nice work. Their paper is down at the bottom there. They're using a tool called MapElites, which is another genetic algorithm, and its job, as well as minimizing a particular objective, is to try and spread out the solutions as far across the search space as possible. It's trying to make a really diverse set of solutions so that you can hopefully get some variation that you can choose from. Although they're all good solutions in terms of your overall objective, it's trying to find ones that are varied in some way. But you can also use this approach for exploring a Pareto optimal set, like the trade-off that I had in the last slide, or an exhaustive or grid search, and that's the context in which I've been using it. So here is that trade-off again for a bunch of building designs, and I'm now going to skip out to my browser, and we can actually represent those using what's called parallel coordinates. So each wiggly line here, and I'm highlighting a few of them now, these are all solutions. Over on the right, we've got the two objectives, and you can see that they conflict with each other. There's an inverse relationship. But then we've got some other objectives here. We've got carbon, we've got overheating hours. So this is for a building, remember. And then we've got things to do with the actual design of the building itself. And the reason that this is really good for improving trust in the solutions is that we can start to make an informed decision about which one we actually want, and maybe start to add some of these implied goals on top. So maybe we'll say, well, we've got a gap here in energy performance, so it'd be silly to take these high energy ones. We'll only keep these ones down the bottom. But actually, having seen that, we've now got a lot of choices for our wall type, and I know that it's really easy to work with this wall type at the bottom. The other two are really horrible kind of concrete that don't set very well, so we'll use those. Right, we've narrowed down our set of solutions a lot, and we can see here that actually we've still got kind of a range in overheating. Well, maybe we've got a workforce that really don't like to have a hot office, so we'll keep the overheating hours down. And then maybe we want the windows to be open as much as they can be, so we'll make this variable a bit bigger. And I don't know, let's say we also want to keep the amount of glazing down, so we're not using air conditioning so much. So we'll pick that one, and now we've got one solution. So we've got this kind of stepwise interactive approach through the different solutions. So where are we at? So that's a few ideas for how we might explain the optimization results that are coming from an evolutionary algorithm. You can visualize them during the optimization. You can make them part of the final results. And the whole idea is about exploring kind of what's important, what's not, as seen by the algorithm. And I'm hoping that it's a nod towards increasing trust, because you're giving the user an informed choice of solutions, or at least why the algorithm has ruled out particular solutions. Obviously very problem specific, and that's where the active research is just now. How on earth do we try and generalize this stuff? And well, there's more philosophical question at the bottom there. Is it explanation? Is it justification? Does that really matter so much? You know, as long as we're able to justify the solutions that we've got, maybe that's enough. So there we are. Whole pile of ideas. I hope that's been helpful to you. Apologies, I've run slightly longer than I said I would. Sorry about that. But there is a bit of time for questions, so please ask away.
Thank you very much, Sandy. Yeah, any questions, please?
I have a question, Sandy, if you don't mind.
Go on, Ken.
So when we're looking at the problem with the windows and temperature and such, how do you deal with the continuous nature of time and the movement of the sun? That data space is obviously continuous because, you know, from sunset and to sunrise, that time is, you know, did you make that discrete and how do you handle it?
So it is discretized. I think it was down to 5-minute intervals. This is one reason that the fitness function was really long running. The simulation that computes energy is 5-minute intervals over a year, and that kind of computes how much solar energy is coming in, but also kind of what people might be doing in the building based on some kind of typical scenarios, heat movement through the different surfaces. It's really complicated, not something I'm going to pretend to understand, but it takes a long time to run. But it is, yeah, my understanding of the solar bit is that it's discrete, yeah.
A couple of questions on the chat.
Okay, so the parallel page, really nice question, and one that I kind of glossed over. How is the order? Yeah, so you're right. It is the relationships between variables. How is the order of the variables determined? Totally arbitrary. And that's one of the most dissatisfying bits about it, because you get a rather different picture if you move them around, right? That really clear relationship that we had. If I come off of this, if I get rid of some of them again, that really clear inverse relationship between the last two, you wouldn't see that if they were spread out. So that is one of the things. I've got an inkling that we might be able to do something with clustering or something around that, but that's actively trying to work out how on earth we do that just now. I see another one. So it's a training data based on informed choice. Oh, the training data is based on an informed choice of solutions found on the online publicly available web. I'm not quite sure what's being asked there. So all of the solutions that are coming here are typically they'll be randomly generated. Sometimes we'll try to kind of cover the space as evenly as we can, but it depends on what the formulation of the problem is. That's where you can set what the variables are. So you say, well, here we've got a real world problem. It's got these bounds for each of these variables, and then it's simply about exploring that space. Could you use a GA to do the ordering? Indeed, that's yes, absolutely. That could be interesting in itself. I've done a little bit of genetic algorithms applied to kind of artistic visualization things, with interesting results, for which you may read interesting as being artistic, for which you may read as being I have no idea what on earth's going on. But yeah, that's certainly something to try. Yes.
Thank you very much, Sandy. Any more questions for Sandy? Something related to what Ken flagged, Sandy. So how do you handle the dynamic aspect if the domain is dynamic and real time?
Yeah, so let's say essentially your fitness function changing over time.
Yeah.
Yeah. I don't at the moment. It has been a bit of a cop out. I haven't got there yet. Yeah, that's so there's all kinds of knots with these problems because I haven't really talked about constraints either. This is where solutions either pass or fail. That's another layer of complexity. But if you've got noise or uncertainty in the fitness function, or if you've got a dynamic one where it changes over time, that's going to make the picture way more complicated again. And yeah, my approach at the moment is to try and at least try to get something for simple problems. Okay. But it's something we need to keep in mind. You're right.
That's good. And in terms of the visualization, any thoughts on how this could be easier? I mean, I'm thinking of people who are not necessarily familiar with the space, so visualization that it's easier for non technical people to consume.
Yeah, I agree, because the parallel coordinates thing that I've got up just now, I mean, it's really good I don't think it's as intuitive as it could be. And equally, you know, a lot of these things where I'm kind of plotting the values of variables is relying on some kind of you know, it's still relying on a lot of expertise. Yeah, that's really the goal. I mean, the buildings one where I was kind of colouring the where the glazing was, that's a little bit better. But you know, because it's a physical space that you're modeling, it's a bit easier to visualize. But you know, that's not going to map over to things, you know, employee scheduling. Yeah, it's going to be really tricky to try and visualize that, certainly in an intuitive way. So I don't know is the short answer. Area of active research. I'm chatting with a psychologist who's interested in decision making just now to try and hopefully make some sense out of these kinds of questions.
Thank you very much, Sandy. Any more questions? Yeah. Great. No, that's very, very insightful. Thanks a lot, and we believe we'll be hearing more from you, Aidan, and others as the years go by, mainly on the work that we're doing with you on explainability. So, yeah, my colleagues, I believe, will join me in expressing our thanks for the talk.
Thank you very much, Sandy. It was a great tour. Thank you.
No problem at all. You're most welcome.
Great. So I guess we'll bring the call to a close then. Yep.
Great. Okay. Thank you very much.
Thanks a lot.
Thank you ever so much, everybody. Thank you.
Thanks, yeah. Bye.